Listen, we want to continue our conversation about the product rule and the quotient rule, and also part of this part 2 video, we're going to talk about higher order derivatives. But right off the bat, I'm going to start with a proof. Now remember proving the power rule. Remember, you know what the power rule is when you say the derivative with respect to x of x to the n is, I have it written right here, nx to the n minus 1. Now, we've proved part of this thing. We proved it when n is equal to 1, and that was a pretty basic proof using the definition of a derivative. We also proved it when n is a positive integer, and that used binomial expansion or the binomial theorem. You might remember that proof. Now, what we want to do is prove this when n is a negative integer. Okay, so here's the proof when n is negative, a negative integer. And then in a later time, we'll prove the final case when n is rational or a fraction. So that's a completely different proof. So here is n is a negative integer. Now to set this up, what we want to do is assume n, we already know it's a negative integer, so we're going to say is negative k, where k is a positive integer. I probably should have been clear and wrote that out to the side. So n is equal to negative k. So I have the derivative of x to the n is the same thing as saying the derivative with respect of 1 over x to the k, right? That means the same thing because n is equal to negative k. Now we want to take the derivative. How are we going to do that? We're going to use the quotient rule. This is the first time I haven't proven one of these using the definition of a derivative. But the good news is now that we have proven the quotient rule, we can just use the quotient rule. And you know it well, low d high minus high d low over low squared. So I take low, which is x to the k, times d high. The derivative of 1 is 0, minus high, which is 1, and then the derivative of x to the k is kx to the k minus 1. Now, why can we say that? Isn't that what we're trying to prove? Well, no, we've already proven it when k is a positive integer. So we are allowed to use that here. And that's over the denominator squared, so x to the k squared. Now, next step, let's simplify. So you see this term is 0. It's gone down here. And then I multiply negative 1 times kx to the k minus 1. And then, of course, when you have x to the k squared, you can multiply these exponents together to get x to the 2k. Now we need to continue to simplify. This is just algebra. So you know when you have the same base, you subtract the exponents, right? So the negative k out front remains, and then you have k minus 1 minus that exponent in the denominator, 2k. The next step is going to be to combine like terms, and that gives us, you know, the k minus the 2k is negative k minus 1. Then, don't forget, we replace n with negative k. So I'm going to remove this k right here and replace it with n, and the negative k in the front, and replace it with n, and we're done with our proof. That proved it. Our answer is nx to the n minus 1. That's what we were trying to prove. Pretty cool, huh? We just used the quotient rule to prove that. Now that we have proven it, we can use it. Fact is, though, we've already been using it, right? But we really couldn't get to a reasonable proof until we proved the quotient rule. But that power rule is pretty impressive. And we've been using it for fractions as well, fractional exponents, but we haven't proven it yet. But it's coming. We just have a later section before we can do a reasonable proof for that. Now what I have for you here is the derivative of 4 of our trigonometric functions. Now we already know what the derivative of sine of x is. The derivative of sine of x is positive cosine of x. And then the derivative of cosine of x is negative sine of x. We proved one of those previously. We proved that the derivative of cosine of x is negative sine of x. And we had to use the cosine of alpha plus beta trigonometric identity to do that. These proofs are actually easier, and I'm trying to decide as I'm doing this video how many of these we want to prove. I guess we could do all of them, but these are worth memorizing. But the fact is, the proof is pretty simple. So if you happen to forget one of these four, I think you could reproduce it pretty easily. So let's start with the first one I have listed. Notice it says the derivative with respect to x of tangent of x is secant squared of x. Now again, that's a memorizer. Yet, what if you can't remember it? So I'm going to start with what we're trying to prove, which is the derivative of tangent of x. Now what I want to do is I want to rewrite tangent as sine of x divided by cosine of x. Okay, so that's one of those quotient identities in trigonometry, and that's the quotient identity, of course, for tangent. Now, how am I going to prove this? Well, let's use the quotient rule. We just learned how to do it. You know, low d high minus high d low over low squared. So here I go. So this derivative is low cosine of x times the derivative of the numerator, the d high. What is the derivative of sine of x? We know it is cosine of x, right? Minus high, which is sine of x, d low. What's the derivative of cosine of x? It is negative sine of x. So those parentheses are necessary. Over the denominator are low squared, so that's cosine squared of x. Now I simplify. So cosine of x times cosine of x we know is cosine squared of x. And then this sine of x times sine of x, both negative, is going to give me plus sine squared of x. This is all divided by cosine squared of x. Now, what do you notice we could do? Preferably, I'd write this vertically, the next line below, but since I'm running out of space, I'm just going to go ahead and move on to the right. Y'all, what's cosine squared of x plus sine squared of x? You know this, right? That's 1. That is the Pythagorean theorem in trigonometric form. Over cosine squared of x. Now, we're almost there. You know what? 1 over cosine squared of x is the same as saying, I think you'll agree, 1 over the cosine of x all squared, right? What's 1 over the cosine of x? That's secant of x. Look. My computer's freaking out again. Stand by. Okay, so my computer's working again. I got 1 over cosine of x we know is secant of x. And since that's squared, I can write secant squared of x. End of proof, right? We got it. Now, I think I have enough space over here to the right. Let's go ahead and jump into cotangent. Listen, I know you could do the cotangent one on your own. It's worth trying all 4 of these on your own. You know the reason why. What if you forget it and you need it? So if I'm going to do the derivative of cotangent of x, then I would start with the definition of cotangent using the quotient property or the quotient identity. That's going to be cosine of x over sine of x. So this is going to work very similar to what we just did. I'm going to use the quotient rule again, low d high minus high d low over low squared. So low is sine of x. The derivative of the high one, the derivative of cosine, is negative sine of x minus high, which is cosine of x. D low, the derivative of sine of x, is cosine of x. Okay, that's all over the denominator, sine squared of x. Don't forget to square the denominator. All right, I multiplied. Sine of x times negative sine of x is negative sine squared of x. And then this is minus cosine squared of x over sine squared of x. Now, what you don't do is cancel these two guys. Remember, you can't do that because you have a binomial in the numerator. What you can do is factor this negative out of the numerator. So it's negative 1, and then sine squared plus cosine squared now, because we factored that negative 1 out of the numerator, and of course of x, over sine squared of x. Now, once again, a highlight for you, this is the Pythagorean identity. So that's equivalent to 1. So now I have negative 1 over sine squared of x. Now, this can be written as negative 1 over sine of x all squared. And we know that is negative And then 1 over sine of x, you know, is cosecant of x. And I'm going to write the square on the inside because that means the same thing. So we proved that one. Again, you're just using the quotient rule, y'all. It's not any fancy proof. There is no trick to this proof. You just use the quotient rule and trigonometric identities, which I know you all know very, very well. And you can do it. So let's go to another page and work on these other two. I may just do one of them. I think if I just prove secant of x is secant of x tangent of x, that might make you happy. And you can do the fourth one on your own. So we're trying to prove that the derivative of secant of x is equal to secant of x tangent of x. How do I start? I rewrite the derivative of secant of x as 1 over, now what is secant? It's 1 over cosine, right? 1 over the cosine of x. Now what am I going to do? Use the quotient rule. So here we go. Now once I start using the quotient rule, you don't need to write this d over dx situation anymore, because you are taking the derivative. So this is the derivative I'm about to write. So low d high, so low cosine of x. What's the derivative of the high? What is the derivative of 1? 0, right? So low d high minus high, which is 1, d low. So what's the derivative of cosine? Negative sine of x over, and this is what people tend to forget, low squared. So that's cosine squared of x. Now I just simplify. Y'all know cosine of x times 0 is just 0. This negative 1 times this negative sine of x gives me plus sine of x over cosine squared of x. Now what do I do? Well, write it a little bit simplified. So that's sine of x over cosine squared of x. Then you might want to look where you're going, right? I'm trying to show that this is the same as secant of x times tangent of x. Is it? You know, you did enough verifying identities in your trigonometry class to know what to do here. I can rewrite this expression as, now secant is written first. So what if I say this is 1 over cosine of x times sine of x over cosine of x? Is that true? Sure it is, right? Because 1 times sine of x is sine of x, and cosine of x times cosine of x is cosine squared. Totally allowed to do that. What is 1 over cosine of x? That is secant of x. What is sine of x over cosine of x? That is tangent of x. And we have proven our theorem. Now when you try the fourth one on your own, that the derivative of cosecant of x is negative cosecant of x cotangent of x. By the way, you notice how all the co-derivatives are negative and all the not co-derivatives are positive? That will help you memorize. But this is going to just have an extra negative in it. The proof is very, very similar. Try it on your own. Matter of fact, pause it now. Go ahead, put it in your notes, get it done. I often ask for one of these proofs on the test. So make sure you can do all 4 of them. Okay, here's a fun problem. Example F, calculate the derivative. So we have a rational function, right? Just happens to have trig in it as well. That's perfectly okay, right? We're just going to use the quotient rule. And there's no way to rewrite this easily. Well, actually you could. Could you? You could use the quotient rule on this, or watch this as I'm thinking about it. What if I rewrite? Always looking for a faster way to do this. Don't always do it. A lot of times I do it the slowest way possible, but we're looking for a faster way. It's the smart way to handle it. I could rewrite this as y is equal to sine of x over cosine of x plus 1 over cosine of x. Now I'm still rewriting. No calculus yet. This is y equals, y'all know sine of x over cosine of x is tangent of x, and 1 over cosine of x is secant of x. All right? Now, y primed, what's the derivative of tangent of x? I have it right over here to the right. Now, again, this is a memorizer, but for now, I have it on over here to the right. Derivative of tangent is secant squared of x. Always check your variable, make sure it is an x you have in there. Plus, and what's the derivative of secant? Well, let's write here, that's secant of x times tangent of x. Now, I am perfectly happy with this answer, but warning, remember how I said if there are any greatest common factors, you should really factor them. So this has a secant of x common to both terms, so let's factor that out. Secant of x, and that leaves me with secant of x in the first term plus tangent of x in the second term. And the reason you do something like that is because derivatives are used for further calculations. You often set a derivative equal to 0. I'm not going to tell you why just yet. You could probably imagine in your mind why you might ever set a derivative equal to 0. But right now, this set equal to 0 is the first step to solve, not the step above. Might as well factor it. All right, let's talk about something new, higher order derivatives. Now what that means is basically the derivative of a derivative. So the first derivative, that's what we've been doing all along. When I've been asking you to calculate the derivative or find the derivative, then you are simply doing the first derivative. But you can take the derivative of a derivative. So notation, that's what this is all about. You've already seen all the possible notation for a first derivative. Well, watch this. The derivative of a derivative gives you this list. It's called the second derivative, appropriately named. That's that y double primed. Okay, that means take the derivative and then do it again. So f double primed of x. Now, if you see this, this is called Leibniz notation because of the mathematician that came up with this notation, one of the creators of the calculus, more like the discoverer of the calculus. But this is, I don't even know the best way to read it. I would just say the second derivative of y with respect to x. That's the best way to read it. The second derivative of y with respect to x. This is the same thing, the second derivative of f of x with respect to x. Okay, and this is a notation you'll learn when you start doing something called partial derivatives, which is not in this course. It's probably in your Calculus 3 course, but this notation is for partial derivatives, and this would be the second derivative. All right, now if there's a second derivative, yes, there's a third. So here's the notation for third derivative. I have an error. Funny how I see it now. I type all this stuff and look again, but there it is. So y triple primed is your third derivative, or the f triple prime. That means take the derivative of the derivative of the derivative, and this is the third derivative with respect to x. This is the third derivative of f of x with respect to x, and then there's that partial derivative notation that I don't believe you will ever see in a Calculus 1 course. If you could take a third, you know, you could take a fourth. Now, things change a little bit notation-wise on a fourth derivative. Notice instead of putting the 4 apostrophes up there, we just write y and then with the 4 in parentheses. Now, that 4 in parentheses, okay, is important. That's telling you the fourth derivative, not y to the fourth power. So you can see where it could get a little confusing. Now, this is, again, the fourth derivative of x. This is the fourth derivative of y with respect to x. This is the fourth derivative of your function f of x with respect to x. And finally, that partial derivative notation. Fifth derivative looks like that. Okay, just like the fourth, but we have a 5 everywhere. And then you could do this for an nth derivative. So you could take a 10th derivative, a 100th derivative. Now what that means physically gets a little weird. But the first and the second derivative have very clear definitions as far as the physical world goes, and we will get into that. So for the final discussion in this video, I'd like to show you an application of these higher order derivatives. But again, keep in mind a higher order derivative is just the derivative of the derivative potentially. What I want you to be aware of is your first derivative has to be right before you can get the second derivative correct or the third derivative correct. So check your work before you go too quickly onto the next derivative. But here's an application of the second derivative. Acceleration is the rate of change of velocity per unit of time. So it's how fast your velocity is changing, while velocity is the rate of change of position. That's just a reminder. So it says, therefore, acceleration is the derivative of velocity or the second derivative of position. So if you're given a position function and you want to find velocity, you take the derivative. If you're given a position function and you want to find acceleration, you take the derivative twice. So we have a problem G right here. The velocity of an automobile starting from rest is, okay, we have v of t, that is velocity, is 100t over 2t plus 15, where v is in feet per second. So you have to have some units here to be able to discuss this. It says find the acceleration at 5 seconds, 10 seconds, and 20 seconds. So if we're given velocity, notice right up here, and we want to find acceleration, it's the derivative of velocity. So we're not taking a second derivative here, just a first derivative. So I have a of t is equal to v primed of t, in other words, the derivative. And how are we going to take this derivative? Well, it's a quotient, right? Let's use the quotient rule. So I have low d high, so that's going to be 2t plus 15, and then d high, so the derivative of 100t, you know, is 100, minus high, which is 100t, and then d low, the derivative of the denominator, is going to be 2 times 1 plus 0, which is 2. Is everybody okay with that? I hope you are. I'm not writing out every single little step over the denominator squared, so that's 2t plus 15 all squared. Now, I'm just going to plug in values. It's asking me to find the acceleration at 5. That means plug in 5 for t, at 10, and at 20. So honestly, you could stop right now and plug in those values. But also, you do need practice in simplifying, especially when you're dealing with the quotient rule. So I want to continue this process and simplify as much as possible. Now, one thing you can do to simplify, most people just want to distribute. But y'all, if you can factor out a greatest common factor, that's the way to go. So notice, look. Here are your terms. This is a single term for the moment, and this is a single term. What do those terms have in common? Well, they both have a 100, right? So I'm going to pull the 100 out, and that's going to give me 2t plus 15 minus, now remaining after I pull off that 100 on the second term is 2t. Okay? That's divided by 2t plus 15 squared. Now, if I continue to simplify, look, this 2t and this minus 2t cancel. I have 100 times 15 is 1,500 over 2t plus 15 squared. So that is my acceleration in feet per second squared, okay? Because you take that derivative again, that's what you get, because you've got seconds down here and you're squaring it, so that's in feet per second squared. Now, again, I'm supposed to plug in 5 seconds. I could have done that at my very first step up here. If you fear simplifying errors, that might be worth doing. But you're not always plugging in a value, and then in that case you would need to simplify your a of t. But we're plugging in a value, so let's do it. So first I'm going to plug in 5. So a of 5 is going to be 1,500 divided by 2 times 5 plus 15 squared. So that's 1,500 divided by, now 2 times 5 we know is 10. 10 plus 15 is 25 squared, which gives us 1,500 divided by, see, 625. And when I simplify that, gives me 2.4, and that's feet per second squared. Now, I've also got where you need to do this for 10 seconds and 20 seconds. We could do that real quick. I'm kind of running out of space, and I know you're totally capable of doing this, but it would be nice to think about our answers. So the acceleration at 10 seconds, that would be 1,500 over 2 times 10 plus 15 squared. So that's 1,500 over, so that's 20 plus 15, that's 35 squared. When I type that in my calculator, you got 1,500 divided by 35 squared, and that gives me 1.22. If I just round 2 decimal places, 1.22 feet per second squared. So what would you say about what's going on here? The acceleration is slowing down, right? At 5 seconds, we're at 2.4 feet per second squared. That's how fast the velocity is changing. Whereas at 10 seconds, we're at 1.22 feet per second squared. At 20, I would guess that the acceleration is going to be even less. And probably as we're getting up to speed, you're accelerating less and less until you just level out your velocity. Seems reasonable, right? So this is the final slide I have in the video. The acceleration at the top is the same definition I just went over. So acceleration is the derivative of velocity, and velocity is the derivative of position function. So what that really means is acceleration is the second derivative of your position function. So here's what I want you to think about. Explain what happens if, okay? So let's just think about this. So velocity is greater than 0. We've already talked about what that means. That means you're either moving forward or you could be moving upward, just depending on what story you're trying to tell with your velocity. And acceleration is positive. Now, what does that mean? So it means your velocity is changing in a positive way. So really what this means is you're speeding up in the forward direction. Does that make sense? So again, the acceleration being greater than 0 means you're speeding up and you're going in the forward direction because velocity is positive. Now what if we change that up a little bit? What if now we think about velocity is still positive, so that still has the forward up situation, but acceleration is negative. So velocity is positive, but acceleration is negative. So how about slowing down, but still in the forward direction or upward direction, depending on what positive actually means for your particular situation. If you're a car, it's in a forward direction. If you're throwing a ball up in the air, it would be in the upward direction. Okay? Now here we go. This time, let's let velocity be negative. Now remember what that means. That means we're going backwards. I want to change colors. Green. So we're going backwards. Anytime you see velocity is negative, you're either going backwards or down. Okay? But acceleration is positive. Now notice these are opposite again. So here when these were opposite, it meant we were slowing down. So if we're going backward, yet acceleration is greater than 0, here's what we're doing. We're slowing down in the backward or negative direction. So that seems weird, right? And by the way, that last word is supposed to say direction. Okay. The last situation. V of t is less than 0. Once again, we're talking backward. No matter what's going on with acceleration, if v of t is less than 0, means you're either going backwards or you're going down. You're going the opposite of the positive direction, however it's set up. But now, if acceleration is also negative, they're going in the same way. Just like when they were both positive, we're speeding up in the forward direction. If they're both negative, then we are speeding up in the backward direction. I'm not going to say direction, but speeding up, going backwards is what's happening here. I always think that's a neat problem to think about. So if they're opposite, basically that means you're slowing down, and it just depends on what velocity is. If it's positive, you're going forward. If it's negative, you're going backward. But if they are both positive or both negative, that actually means you're speeding up. And again, that's either going forward if velocity is positive or going backward if velocity is negative. I hope this helps. There were no examples of calculating multiple derivatives, so I'm going to go ahead and add one more page to this just to help you think about this and work on notation. So one more problem, just going to write it out. Hold on. So what if we have the problem that f of x is equal to negative 5 cosine of x? And what if I ask you to calculate All right, f to the 5th. Let's make it to the 6th, since I already have a 5 in my problem. f6 of x. Now, what in the world does that mean? It means the 6th derivative, right? So let's see if we can use correct notation and knock this out. So f prime of x, the first derivative, what's the derivative of negative 5 cosine of x? Well, the derivative of a constant multiple, remember, you just bring that down, negative 5. And what's the derivative of cosine of x? Negative sine of x, right? The derivative of the cos is a negative result. All right, so you may want to simplify that. So negative 5 times negative 1 is positive 5 sine of x. There's your first derivative. Second derivative, again, proper notation, that's the two apostrophes are double primed, if you like. The derivative of 5 sine of x is going to be 5 because of the constant multiple, and then the derivative of sine of x is cosine of x. Okay? The third derivative of x, the derivative of 5 cosine of x. So the 5 comes down. The derivative of cosine is negative sine of x. That needs to be simplified, be negative 5 sine of x, right? The fourth derivative, that's when you use the parentheses around the 4. And I'm taking the derivative of the third derivative. So the negative 5 comes down. The derivative of sine of x is positive cosine of x. So the answer is negative 5 cosine of x. The fifth derivative, this gets old, doesn't it? But you got to be careful, because if you mess up any of these, your final answer is certainly going to be wrong. The derivative of negative 5 cosine of x, the derivative of cosine is negative sine, so negative 5 times negative sine of x is going to give me positive 5 sine of x. One more time. So the sixth derivative of x, okay, so 5 sine of x is where we are. The derivative of that is going to be 5 cosine of x. And there's our final result. Okay, I hope you guys have a wonderful day, and come back and visit me for the next section, which is going to be the chain rule.